Hello fellow skeptics, this is Nayhm, and welcome to the third video on the broad topic of what's wrong with physics, modern physics, and how can we fix it. My working hypothesis has been, and I've proven in one instance, that we've missed things in our basic physics. I call it Newtonian physics, but at this point the first anomaly or missed physics had to do with orbital angular momentum. That really wasn't something that Newton was familiar with or worked directly with. But the orbital angular momentum, using the center of mass of an object as its sole physical characteristics, was shown to be an approximation. Now, it's had effect. There are a series of things that we could look at and redo in the context of using the exact form rather than the approximation represented by the point mass assumption. But now we get a little further into the story. One of the virtues of using a point mass, as was shown in the the second video, is that it reduces many things to just simple algebra, multiplications, and most of the calculus is fairly simple. The elementary calculus is sufficient. The relationships are what we call analytic, at least the way I looked at the problem. Analytic means that you can get an exact solution. However, once I discovered that there was a consequence to using the center of mass, I went back to Newton's most famous work, which is his Principia Mathematica. And I took a look through it at the point mass where he used it and talked about it. And one of the key places he used it is in solving the Kepler problem, the orbital equation, planetary orbit models that he developed. And he also used the point mass model in developing his law of gravitation. And so, based on the fact that the orbital angular momentum is only an approximation if you use the point mass model, then since he used that same point mass assumption or model in developing his law of gravity, the question was, is that a simplification? And if so, what is the exact form for the model? What should it be? What could it be? And so I took a look through the Principia Mathematica and found a statement, a very succinct statement of what Newton said he was going to be doing, or how he viewed gravitational interaction between objects. And from there, we took a look at the statement and set it up mathematically, and the mathematical model does not match the simplification from using the point mass model. It's more complicated. The virtue of the point mass model, at least for the law of gravity, is it again reduces things to algebra. Whereas if you use the exact model, which I'll discuss in just a few minutes, you can't use algebra, just algebra. You have to use calculus. And Newton's calculus at the time was not up to the task. So with that, let's take a look at some of the slides where I lay out the exact gravitational law as Newton intended it to be, but which he did not actually find. Once the problems or issues associated with using the center of mass was identified, and the orbital angular momentum was shown to be, using the point mass approach, to be an approximation, I went back and looked at the Principia Mathematica, Newton's most famous work, to see if I could identify somewhere else where the point mass concept was used. I discovered in that same area where he talked about the orbits, the Kepler problem, the planetary orbit issue, is this statement from his Principia. And this is how he explains or describes what the mutual interaction, gravitational interaction, would be between two extended objects, in his case, uniform spheres. And so many physicists, a lot of people have read this, and they don't have a problem with this description. It's a good description. And if we take a look at what it means when you render it into a mathematical form, or at least a graphical form, you get this. You get uniform spheres, you get mass element in each one being attracted by the mass element in the other, and you have all these pairs that you sum up and add up that make or describe what the mutual interaction is between the whole objects. And R is, of course, the center of the distance between the actual physical centers of mass of these objects. So this is where that statement leads us, and we don't have a problem with this as being a pictorial representation of what Newton was describing. However, he couldn't solve that general problem. So what he did was he used a concept that he was very comfortable with, and we are too, perhaps unfortunately, and that is the idea of the center of the mass. And so what he did was he reduced one of the objects to a point mass. That point mass is located at the physical center of mass of the object. And then he proceeded to set up the problem of a mass element in the remaining extended object being attracted to that point mass. And he then proceeded to sum up all of these mass elements that were being attracted to this point mass. And what he got was effectively a statement that said you could consider all the mass of this first object also located at its center of mass. And what we've done is extrapolate that, inductively extrapolate, perhaps erroneously extrapolated that to saying any object, no matter what its size, shape, orientation, distribution of mass, can be described completely by putting all the mass at its physical center of mass. And the same with this object, whatever it may be, and that the mutual gravitational attraction between these two objects can simply be given by knowing what these two masses are and what the physical separation is of those centers of mass. Despite what the words were that Newton stated in the Principia about what he was going to do, what he actually did using his early graphical techniques for performing integrations or summations, this integral sign is a stylized S for sum, was he set the problem up this way, of taking one of the objects simply as a point mass and then calculating the summation of the volume, rho dV as a mass element, across all mass elements within the sphere that he was integrating, and that gave him simply the mass of the second object divided by the distance between the two centers of mass. That's not what that description in the Principia actually requires. It requires a summation, simultaneous summation across both extended physical objects without reducing it to a point mass. And this is in cylindrical coordinates, describing the two objects in cylindrical coordinates, having a common axis joining their centers of mass. And this is the same thing rendered in spherical coordinates. As you can see, these are very complex. Newton couldn't solve the problem, which is why he reduced one of them to a point mass, which was a legitimate, in his mind, simplification. These are not analytic. They don't have a complete solution. The only way they can be solved is with a computer and using numerical techniques, and having sufficient software to be able to carry out these calculations, and the computers who are powerful enough to carry them out, is something that's only occurred in the last half century. And in fact, within the last 20, 25 years, have the calculation such as he's been able to be carried out by uh, almost anybody who has a computer and the software. In my case, I use Mathematica as a software. That didn't exist more than about 25 years ago, nor did the equipment, the desktop computers, laptop computers, just simply weren't powerful enough. So these are the exact expressions. And just to see where they come from, this is in cylindrical coordinates, and what we have here is a sphere here and a sphere here, separated with their centers separated by distance delta, and we set them up with mass elements in each object, and we carry out the summation or the integrals across both objects simultaneously. Very complicated, but doable. In my case, I used Mathematica user community and consultation with faculty engineers who did use Mathematical to make sure that I was setting the problem up correctly. There is a syntax that you have to learn, and some things are not intuitively obvious, so there is a learning curve, and you have to test it to make sure you're using it correctly. So when we go ahead and apply this, I used a particular example. I used the example of the Earth and the Moon to find a statement for the mutual interaction between the Earth and the Moon as two extended objects and not as point objects. And the separation here is in terms of the smaller object, the Moon, and its distance from the center of the Earth in terms of Earth radii. So the actual separation of the Moon from the Earth now is, let's see, this is 60, 70, 80, 90, 60. So it's right in here between 55 and 63. This is the actual distance now of the Moon from the Earth. So this is where we are now. I extrapolated backwards to see what the mutual force may have been in the distant past, and you actually can't get back this far because the Roche limit would cause the Moon to break up. It couldn't remain as a solid object if you got in closer than the Roche limit, which is somewhere right around in here. So this represents the various interactions between the Earth and the Moon as the early Moon slowly spiraled away from the Earth, as it is doing now, until it's out at this particular point. This represents the current location of the Moon relative to the Earth. Now, you'll notice that there's some scattering in here, and this was consistent no matter what coordinate system I use, spherical or cylindrical. And this strange anomaly of these points being up here, that also stayed nearly the same regardless of the coordinate system and regardless of precision and any other variations I can make in terms of how to carry out that calculation. This is either an anomaly of the calculating process, or this is something that may be real and idiosyncratic with respect to the relative ratio of size of the Earth to the Moon and the particular distance at this particular point. What this says is that the mutual force between the Earth and the Moon in this particular area does have some fairly substantial variations throughout the orbital of the Moon around the Earth. Even though it doesn't orbit that way, this is the relative relationship of the Moon to the Earth during the times. So this scattering of points stays more or less constant regardless of how you carry out the calculations. And this strange little anomaly occurs there. Now, whether or not this is a function of something that's going on within Mathematica, where the algorithms are proprietary, or whether or not it's a real phenomenon, very unusual. And so this represents a deviation of the results of the mutual force using the general law versus the point mass law. And you can see that there's definitely a perturbation. We know that the orbits, which are elliptical, unless you have exactly an inverse square mutual force between the centers of mass of those objects, the elliptical orbit doesn't stay stationary. It in fact doesn't exactly repeat on itself, but in fact does what's called precessing. It would be the perigee, which is the closest approach to the moon's orbit to the Earth, is the perigee, and that point will move relative to its prior point each revolution, given by a small amount. And these are very small perturbations, but there's been a lot of orbits of the moon around the Earth. And so there's an accumulation here, and it causes that ellipse to precess. So we have the Earth and the moon is known to have some unusual orbital characteristics that are not fully explained using the current approach using point mass for either the mutual force or for the angular momentum. And you can see that there are reasons why the Earth-Moon relationship is more complex than just given by the point mass model. This also raises another interesting point that says if we don't really understand the behavior of the moon's orbit about the Earth, then we really can't use what's happening with the moon or the Earth to justify or to validate various things like general relativity. We do laser ranging on the moon. We see certain variations that are occurring in the moon's orbit, and we use these because of the size of those variations are similar to the sizes would be predicted using general relativity. So we think that that's what we're getting is some validation of general relativity. What this shows is that's not true, that we need to be a lot more careful before we try and validate one theory using the results of what we think is the physical model for another system. So what do we got? Why have we stayed with the point mass model? Well, we thought the point mass, the center of mass concept, was 100% valid. And we didn't really have much of an incentive to look elsewhere because it seemed to work and seemed to work very well, despite the fact that there are, as we'll show in the next video, there are cases where we can't explain what we're observing. But the fact is, the point mass model is simple and easy to use. It renders things into multiplication and simple algebra rather than using complex integrals. However, we're also taught that Newton's model for gravity is accurate. I mean, it's a done deal as far as we're taught and everybody believes. And consequently, there's no career path in questioning something considered completely known, right or wrongly. We're discouraged from looking too deeply into these. It's a failing of modern academic physics in not questioning everything, including those things we think that are completely understood. At this particular point, these models are used by engineers, and they don't really have the same incentive as physicists to dig deep into the underpinnings of some of the various physics that they're using. But we also have another factor here that maybe needs to be considered, and that is the point mass model supports the narrative that Einstein discovered a deeper gravitational law that explains things the point model does not. If that's the case, then why would we go back and look at Newton's point mass model? Because Einstein's model seems to answer some of these observational questions that we're asking. So what we've shown is that there is another gravitational model identified, at least verbally, by Newton. Many Nobel laureates and other scientists have seen that. They don't have a problem with that particular description of how two objects, extended objects, would interact gravitationally. And yet they were willing to accept the idea of reducing one of the object to a point mass was legitimate. And for 300 years, we've believed that that is a correct approach to modeling gravitational interactions. And orbital angular momentum is another case. You have to take these things case by case. What we've done is we've dug into the underpinnings and discovered that there is a more complete model. I'll call it Newton's general gravitational model. In the next video, what we'll do is show in specific instances where we've been having difficulties coming to grips with the way Newton's point mass model describes the gravitational interaction of objects. We've made observations and they don't fit. What we'll do is we'll address it, and we'll address why they don't fit. The observations don't fit the point mass model, and then we'll apply the general model to identifying some ways to really get to the underpinnings of these interactions and to see what the consequences have been of not knowing how to actually describe why these observations are what they are. We've invented new physics, or we've simply lived with what we've gotten and puzzled over it and moved on. My name's Nayhm, and stay skeptical. And in my next video, we will look at some specific examples of applying Newton's general law to problems of current interest.